scusa,
no, cioè tu leggi fino a quanto vuoi leggere, tu hai un calcolo di 24, io leggo fino a 1024, punto.
ma se non ti rimanda, prima mi sono bloccato. Cioè, io per dire no, avevo fatto un vettore di 50 metri, che ho detto tanto sì, più il numero del file 50 mi dovrebbero bastare, però per dire, stesso file manda solamente questi.
Si blocca sulle righe.
Eh sì, poi si blocca, cioè il file manda solamente questi, sono 21 byte. Si rimaneva bloccato sulle read perché si aspettavano tutti quei byte che non arrivavano.
Non vorrei. Io provo a leggere.
So everybody knows that you will send send me an email with the information and I will send information to everybody to see where it is. Okay. Okay. So this part. Illustrates which are the good steps when you switch on your computer. So you know that in a program of read-only memory, there is what is called the basic input-output system that allows your computer to be, first of all, tested and to see which are the components, the current components, and then through various steps to finally run a kernel. How? So, as you remember, each file system has a master boot record, and this is the first. These are 512 bytes that are loaded by the code in the BIOS. We will see that it starts from a known location and immediately jumps to another one, where it must be a code that is supposed to load this master boot record and then to pass the control to the instruction in this master boot record. So this master boot record, you typically have one of the loaders, typically Grub or Linux Lilo, the old one. So this code is the one that look for an image of a kernel and then run the kernel. Running the kernel, in all this part, we are using the CPU in real mode, or without rotation. Then it switch off, switch on the protected mode, setting register as a matter of fact, and this allows to initialize the tables of the kernel, the interrupt and so on, and finally it allows the kernel to run the services and run the first user. So this is the layout of Intel architecture. So you see here that there are various regions. The important information here is, so far, is at the bottom part of this layout, because this is an heritage of the first Intel architectures that simply had 1 megabyte of memory. Okay, so the first DOS machines were had only 1 megabyte of memory, and in this case you see that the low memory was the memory devoted to the user, and in this area there was the BIOS lowly memory, and here the 60-bit devices. Now, and here the VGA display. This low part of the layout has been kept also for the new versions of Intel architecture, 386, etc. And what was added is the 32-bit BIOS and memory mapped device region in the higher part of the memory. So let us see what more in detail what does it mean. So the 8088 had only this possibility of addressing 1 megabyte of physical memory, and only 640 kilobytes. So here you need a little bit of binary mathematics. So here you have 12 zeros. So A means 1010, okay, and then we have okay, 12, so 13, 2 to 13 and 5. This is read as a 5. So 10 times 2, 12, and gamma to 640 because
should be 16 zeros.
yes, yes, these are yes, 16, 16, so 17. Thanks. So this is 10 to 16. It means 10 to 2, 6 to 10. So this is kilobyte and this is 64, and that's in total 640 kilobytes. Okay? By the way, okay, so the BIOS run from this F000 to FFFF. That is the last location. So in total 1 megabyte. What does the BIOS? The BIOS simply performs some self-test on power on and checks essentially what you have on the bus, which is the amount of memory, and so on. And then at the higher level loads the operating system. But we have to see how it does. The extended part of the BIOS is located, as I said, in the high level, high number addresses. Okay, so in the terminology of Intel, there is a hole here from the end of the BIOS region up to this 32-bit BIOS memory device. Okay, so what happens when the CPU runs in real mode? It begins starting always at this location. So rather than starting from 0 at the reset, it starts from this instruction, this location. In this location, it's just written jump far on this other address. Okay? We can follow exactly this bootstrap part of the process bootstrapping part with the QEMU. For people that loads the virtual machine image that I gave you, you have also then to check that you have a assembler, a debugger called DDD, otherwise you download, and a QEMU. In laboratory they are installed, but in your computer you have to check if it is there here or not. So using QEMU, we can follow, if I have time now, I will show you. You can follow these steps. So it does this jump far, and as you can see here, this jump far means that the address that uses by jump is composed of a segment number and an offset inside the segment. So the segment is F00 and the offset is 050. This is a real mode instruction, and the physical address, okay, translates simply in this way. The segment number is shifted. It's multiplied by 16, so it's shifted by 4 bits, and the offset is added. So this F00 becomes F000, okay, one more 0, plus E05B, and the physical address is this one. Okay? So in real mode, the segment plus offset is simply translated by the memory management unit trivially in this way. Okay, in real mode, there is no protection. What does it mean? It does mean that we don't use the segmentation mechanism of the protected mode. Let us see what does it mean. Yes, here. So all this stuff is in your this week or in laboratory directory for this week. So the translation of the logical address to the physical address in the Intel architecture. I have another maybe better slide. No, this, I have one. Nice. Oh, it's not the little one. Okay, by the way, oh, it's a nice one. Okay, so you have the CPU that generates the logical address with a selector and offset. Selector is not segment. Okay, selector is a number that includes information about which kind of address is it. So if it's an address for an interact table or a global description table or for a local description table. The same translation produces the linear address and possibly the linear address is mapped by the page translation to the mapping mechanism. So the selector is an offset inside one table, maybe a global description table or a local description table. Okay, this is a table as the one that I show you, talking about the theory of segmentation. So in the entry we have the protection mask, the address right, the access right, base and limit. Then with the base we go on the linear address. For 32-bit we have the division by 3 because we have a directory page table, okay, where we use this offset to get the initial address of a page table. The second part of the table, another 10 bits, select one entry, and finally we reach the frame number, okay, the final address. The pages, as you see here, are 4 kilobytes. Notice here this register CR3. CR3 is set When CR3 is set, it indicates that the paging mechanism is enabled. Okay? So rather than using directly as a physical address the linear address, the MMU must be prepared to these tables to translate this way the address. There are a lot of flags on this information, a lot of information in this page table. Now I have no time to describe all of them because they are not important for you, for your laboratory. But here you see some of them. Present is the valid invalid bit. User or kernel page, writable or not. Accessed, remember, for reference. Dirty for unmodified, remember the 2 bits. The page size, so the granularity of paging normally is 4 kilobytes, but it may be 4 megabytes. Then, there are second order. The other important information on the CPU are the flags. The flags are all the bits that are set by the CPU. For example, the 0 flag after a comparison for 0, the sign, the parity flag, and so on. This information is stored on context switch and reloaded on context switch because it represents one of the important registers of the machine. Then you have these control registers. CR3 is the one that I said that enables the paging mechanism, and CR0 when you want to pass from real mode to protected mode, you have to set this protection enabled bit here. Okay. The selector indicator are kept into registers. These are the registers of the Intel architecture. So the code segment, data segment, EFG registers, and the stack segment. Okay. So each reference is done through this register that contain the selector index plus these 2 information: the table index, global description table or global description table, and these 2 bits represents the privilege level. What is this privilege level? As a matter of fact, in Unix you use only 2 levels, 0 and 1 for kernel and user, but there is the possibility of having 4 different privilege levels. What is a privilege level? Of course, some instructions are possible in kernel mode and are forbidden for the user mode. Okay, so when you are in user mode, you cannot execute some instructions, and when you go to the kernel space to a system call or an interrupt, the requesting privilege level rise to the one of the kernel. And when you return from the system call or from an interrupt, of course, this flag, this number resets to the user mode. Okay. So, yes.
What is the difference between kernel mode, user mode in comparison with real mode?
Okay, kernel mode and user mode, the question is, what is the difference between kernel mode and user mode with respect to real mode and protected mode? They are two different concepts. Kernel mode means that the CPU may execute whichever instruction, okay? While in user mode, for example, in, out, or modifying the resistance is not possible. So it is one of the protections of the CPU. While real mode and protected mode is different in the sense that you run in protected mode even if you are a user. It means that every address that is generated passes through this mechanism of segmentation that limit your access. So if the segment is code, for example, you cannot write.
Which is the mechanism that follows the segmentation point?
Yes, for example. Yes, because you are going to in a segment that is outside the limit of your domain here. Okay? So base limit, if you generate an address that outside the limit, it is cached.
In real mode, we can also write the kernel device.
Yes, if you are in kernel, yes, initially you are in real mode, and of course you can set up the interrupt addresses, whatever you want. So there are two different concepts that you mentioned. Okay, so we run at reset in real mode, but in kernel mode.
Instead, when we call, for example, a system call,
Then when we are in protected mode, okay, so after setting the global description table, after setting the interrupt gates and so on, we pass to the protected mode. In the protected mode, the segments are flagged as user or kernel again. So if you try to use a kernel segment, you will get a threat. Okay. So in real mode, you don't have the translation or paging, and when the virus starts, as I said, it does a check, initialize the peripheral bus, and sets up its own page table. Okay, when the device runs, it has its environment. Then logically, it looks for a bootable device and then finish this boot process by passing the control to a kernel. So in the master boot record, there are some information and a code. Okay, the code, initial code. The important information here is the BIOS loads the content of the master boot record into this fixed location and jump to this location to execute the code that is here. So we typically put the code of the group bootloader. I will show you in a moment is an example of this code. So, which are the steps? We know that okay, the first operation of the bootloader is to load the master boot sector, and if we look at the instructions of the grab in this range of location, we will see that there are some interesting instructions. So let's see now. Okay, in particular, the grab bootloader has two parts because, of course, these few bytes, less than 512, are not sufficient to do useful operations. So there is a grab stage 1 part that loads the second part, and in turn it will load the kernel. So let us how we install the group to an hard disk image that is bootable, and how we create a minimal kernel, and how we add this kernel image, and how with the bug, the grab will be done in laboratory, but I try to give you here an idea. This is the listing with of the stage 1 of the grab. As you can see here, it starts at location 7C00, fixed, and the first instruction simply jump here. This is the clear interrupt instruction, so it works with the interrupt disabled. Then there are some tricks here for a bug in the BIOS of Intel. So it's a known strange thing. But what is important is that finally it jumps at this segment 007C 50. This XOR A X exec means put 0 on this register A, data, stack, and stack pointer is set to 2000, and then it loads this address on register A. But what is interesting for you is to follow with QEMU these steps. Your grab stage 1 will be similar to this, so there are maybe small differences in the address. But following the instruction in the laboratory, you can breakpoint and debug this this bootstrap mechanism by saying each character coming on if you breakpoint in a given location, and then we will see how the control is given to the kernel. So the tools that we will use is this QEMU, So. Okay, QEMU is an emulator of a machine where you can load a complete Linux, for example. But we will use it together with a debugger to follow step by step the evolution of this coding mechanism. So, which is the debugger that we will use? It is called DDD. So, I'll show you one minimal kernel that I built. So, first of all, I use DDD. Show you what is. So DDD is simply the GDB debugger with a nice visual interface. What gives us this DDD? The possibility of looking at the code and also at the assembler code. So let me follow the steps for generating a kernel here. So cd source cat main.c. So the main.c is simply composed of a single instruction. Return this mask, this sequence of bytes on register A. So this is all that our first kernel does, only this. But it's interesting to check out the steps because on laboratory you have to do then paging. But let us go on. So cd cat build. So cat build is a command that cd on source make use the makefile configuration that we have in source. Then with this object dump command is important. We will obtain the make kernel file, and with this command object dump minus the kernel, the listing of the kernel, so the one that will allow us to debug or to understand what happens. So ls source cat source makefile uses this flags, okay, with some no standard lib because we are not using, we are creating a kernel, there is no standard lib here. The flags for the linker as given here, the flag for assembler given here to create what is called an elf executable of a particular format. And well, at the end we use the NASM, that's why we need to have it, and what we get is kernel kernel image. So let's say go super user or sudo. Okay, sudo. Okay, this is not important. So, build. And build needs nothing, should be src. Okay, first of all, it creates a kernel assembler and kernel. So more src. Kernel. More kernel. .sm text. Okay, so here you see the code, and it's an F format, and you have the text. It does set interrupt here, and then what we understand here is that we clear the interrupt at the start, and then we call the main program that's written in C, and that's all. Then it jumps at 27 somewhere where it does nothing. Okay, because it's never exit, of course. So at this point we will only generate the kernel, but we have to generate the image. The image, when I say image, I mean something that you can put on a pen drive or on a disk, and then you can bootstrap exactly a PC. Of course, we use always the QEMU to be able to rebootstrap without rebootstrapping the machine. Okay, which are the steps? Which are the steps? Okay, I anticipate a laboratory. Okay. I have prepared a pack.shell script that does the job for you. So we did so far this part. Okay, we created the kernel. Now we have to create the image, including the graph. This is done by this pack.shell. And pack.shell does a lot of things. This in my directory. Okay, so the usage is pack and a number of kilobytes of image, typically 256, that's okay. So there's some comments here to remember which is the user, and let us begin with the first of this instruction. Okay. So the first of this instruction is disk dump. DD is a command to copy byte by byte from one device to a file, from a file to another file. /dev0 is a special file that simply generates zeros. Okay? If means input file. So with this DD we want to create in the out file hd.image zeros, simply 512 bytes, but with an offset from kilobyte, 256 kilobytes. Second command that you probably don't know is low setup. Low setup means loop setup. Is an interesting command that allows you to see a device, so to like mounting an image, a file, a normal file on a device file. So this low setup allows you to perform operations that are normally done on devices on a file. So the next command is to create an fdisk input. Fdisk is a command to partition and manage disk disk partitions. So fdisk allows you to create partition, to set their type and define many arguments. Okay, so as you can see here, we have this command that you should know. So this is the output, and this is the here mode. So it means that we give the command that we give here the command that we could want to give to fdisk, and this is output on fdisk input. So to the fdisk we want to say X. Okay, this is standard mode. Then add number of heads 16, sector 63, and AOF corresponds to this keyboard. So this command means create this sequence on fdisk.input. Okay. Then we append the number of kilobytes, because the number of cylinders is exactly what we want to add. And then again we add RNT1. We will see what this number means. 2 blanks, and then A1, etc.
How can we type end of file?
Sorry?
How can we type end of file?
No. End of file is just a word. You can say, for example, people, whatever you want.
Ah, okay.
So
it corresponds to
is a keyword that must be mentioned here. Okay. So finally, you do fdisk giving us input fdisk.input. Fdisk works only on devices normally, okay? So, but since we have done a low setup, fdisk is glad to work with hd.image, okay? So normally fdisk works with images. So for example, let me show you. I keep all this stuff here. and I'll show you. So to use in another window, to use F-disk, you must be super user. Root is the password for the super user. And if I say F-disk, of course it complains because it wants to have a device. So I can say, since my devices are in disk SDA, F-disk /dev SDA. Okay, so I have a command more for help that gives me the latest that you saw. Extra functionality for the first line, for example. Then P to print the current partition table. Okay, so I have 3 partitions, one for core, one for the Linux, and one is extended. So if we look here, X means extra functionality, extra mode. So I go here, X menu for help, and you have another set of possible commands. So H, as I said, the change number of X. Okay. So what I get here, H, implies that I have to give a number. Okay. And the number that I give is 16. Okay, so next I define the number of sectors. 63 is the default, so I can give just a vector. And okay. Then C is the number of cylinders, and for example, I define 256. Okay. Now, the next command R, return to the main menu. N means creating a partition, a new partition. P is for primary partition, which number 1. Then is already defined. Of course, I will not write on my partition, otherwise it would be a problem. Okay, but you understand that I create a partition. A means bootable. Make this partition bootable. Partition number 1, and finally write. So when I write, if I do write, I change my partition table. I don't want to do it on SDA. I want to do it on the image, HD image. So this is the first part, where the key points are the creation of zeroed file, HD image. Flow setup to allow F-disk to see image.h, HD.image as a device, and then F-disk to create. So at this point we just created the partition. Okay. Then how does proceed this? Okay, the F-disk minus L minus U. L lists known partition, and U change display into units. So in this command, what I want to do is to take the number of blocks of this file. So I do this at disk minus u minus l on dev loop 1, and with this set of commands I get finally the number of blocks. Low setup minus d means delete, so I reset the dev loop 1, and I create another association here, low setup with a block with an offset and a size limit. Okay, and I low set up this time slash dev loop 0. Again, I'm mapping this offset of the HD image with a size limit on slash dev loop 0. Then this is the part where I can create a file system. Okay. Again, you can create only a file system, not in a file, but on a device. Okay. The second part creates a menu list for group. So I fill a menu list with these sentences. I call a minimal Linux like kernel. Kernel with this information, and that's all, because I don't use additional say memory that is needed for other. Okay, so this is just create a file with this information for grok. Now I can mount the device that is always this hd.image to mount point. This is a directory, normal directory in my computer. Okay. In this directory, I mount exactly this device root 0. Then I create a directory mount point boot grab. Minus p means that I create all the directories if they are missing, and then I copy grab stage 1 and grab stage 2 menu list on this grab directory. Okay. So far this operation simply copies these two files on this grab directory. Then the next step is to copy the in source kernel, so our kernel we just created, on point boot minimal Linux like kernel. I can mount the mount point and remove all this information, because what I needed was already copied. Detach the loop 0, and I create the grab input file. Again, the same strategy, no cut. The first line must contain device HT00, hard disk image, and we add the grab input the geometry of this disk, because it's C as a disk. We say that the root is HD00 and set up HD0 is the normal instruction that we give. Then finally we execute the grab bin on this grab input, and device map null means we are not interested in device map. I change the owner for all the log file, pack1, pack2, and to HD image, and that's all. Okay, so pack in this way, to summarize, the kernel has been compiled with a build. We created this HD image. We properly make file on the second part of this file. We add initially a grab that contains grab 1 and grab 2, and the menu that is used then by grab 2, and we are ready to run. So, okay. This will be given on. Then, now it's time to run the emulator and the debugger. So, in the directory that you will install the virtual machine, you will have cat.gdb in it. So this .gdb init is an initialization file for GDB. What is important here are the two last lines. Okay. So it says that if we run DDD without anything, we will load the src kernel single file. And the other important things are this. So these are all commands that we would give directly by hand to GDB or DDD. This is done on the initialization file .gdb. So what we do here just to print this information, but the command, the important command is target remote localhost 1234. So what happens? It happens that we will run a QEMU, but suspended, and taking commands from DDD. Okay, so I can run a QEMU as it is, okay, or run it suspended and use the debugger for giving the commands. So let us see the QEMU.shell or first compile. So sudo, we said back slash back shell okay. So he did all the stuff for us, and now cut QEMU shell. I run QEMU without this information, minus suspended, etc. So QEMU minus HDA, $1 is HD image, minus serial monitor standard IO. And you see that grab a run, and that's all in this case, because you don't have anything to see. Oh, here you have just to exit. Instead, if we run with this minus S and this TCP GDB and TCP 1, 2, 3, 4, it means that QEMU runs suspended. This minus S means suspended. So if I say dot slash QEMU shell HD image, okay, it's run stopped. So I can open another window, for example here, quit, exit, root, CD, NK, CD, no, STP, NK, Genesis, and I run DDD background. This time I see the code, return of the main, and the corresponding assembler code. That's why we use this debugger. If you can read here, you see that we are exactly as I said at the top of the virtual memory. So a segment F000, FF0, where there is the long jump on the F00, 0x, E05. So you remember that this will sum these two, shifting the offset. So we can use the command step E means step instruction, assembler instruction, while step means step of one line. And of course we can use a breakpoint and look at the progress of this program in this way. So just to let me see, break at line 7. Okay, put a breakpoint and then continue because it's already running, and it doesn't work. Because QEMU is waiting, but probably is not has been completed well the something happens that the bug shell doesn't succeed very well. Okay. Let me see if it is working here. Okay, it doesn't work. It depends essentially on some timing with the removing the no. What? I will check maybe. Oh, no. This time it works. Anyway, okay. I will be prepared to show you what you have to do on Wednesday. Okay. So in the side of the course you have several files. I will add other for the laboratory, and so if you have time to read them before, you will be faster for carry on of the labs. In the last exercise, as a matter of fact, is still on concurrency, where you use a simple barrier. Okay, so you have to multiply some vector for a matrix, but it is not difficult. Okay. Well, see you on Wednesday.